Welcome Christoph for the kind introduction. I'm Lena, this is my colleague Manfred, and we're presenting a paper today that we wrote together with our colleagues Tobias Reitinger and Fabian Böhm at the research group of Günther Pernol at the University of Innsbruck. It's really fantastic to be here in person, so thank you everyone for the organization, and let's go. Everyone in this room is aware of the fact that humans bear a tremendous potential to improve cybersecurity. Yet, organizations face problems to seize this potential. HAISA spread as an annual report investigating this matter. Last year, 2021, they estimated the cybersecurity skills gap to over 3 million unfilled positions worldwide. This leads to numerous problems, some of which you can see behind me. For example, slow patches of critical systems, which in the past has led to some of the most severe cyber attacks. One approach to address this problem is to provide cybersecurity training to educate future cybersecurity experts. Our field of research here is training in cyber ranges. Cyber ranges are authentic environments for cybersecurity training. Here in those environments, you simulate or emulate systems, so parts of networks or applications, to provide an isolated and highly realistic environment in which you can train participants. As it might suggest, simulating those environments in a realistic manner and also conducting those exercises is time-consuming and therefore costly. And for this reason, we want to make this effort as effective and efficient as possible. So this time that goes into it and all that money doesn't just go to vain. When we conducted cyber range exercises in the past, the feedback we got from the participants was that some tasks, some hands-on skills they achieved, like some tasks they solved, they have problems with the syntax that was lying behind this task. So many cybersecurity tasks are somehow syntax-based. This could be like programming, or configuring systems, or writing config files, or using a command line tool which is new to you. So our participants told us that sometimes they had like the right solution, but it wasn't correct because they couldn't get the syntax right. This can at times be, a bit complicated for them because they try to do it right, but then it isn't, which is highly frustrating. So we were looking for a way to make this better. Maybe reduce that syntax component of training, so separate semantics from syntax, getting it like the right solution first, and then learning how to express it correctly, syntactically wise. The approach how this is done in computer science education are visual programming languages, so-called VPLs. In visual programming languages, you use graphical elements, the ones you can see here, that reduce syntax from programming. So you click and drag and drop those reusable, colorful components, and which is then translated into actual syntax, like Java or Python, for example. What we wanted to do is to investigate, does this kind of programming have the potential to facilitate cybersecurity training as well? We did this by integrating a visual programming language called Walkway into one of our existing cyber range training. And let me quickly explain to you how this is set up. In this training, it aims to educate future security experts to work as analysts in a SOC, in a security operations center, and therefore work with a CM system. For this matter, we simulated an industrial environment, so a factory, which is under attack during the training. During the training, this industrial system produces live data, which suggests the attack. And this live data is fed into the CM system you see on the left-hand side. On the right-hand side, this is the learning management system the trainees interact with. So here they solve several tasks. Like here you see how they are creating a CM rule, which is automatically detecting one of the attacks that is carried out against the industrial system. This rule, when it's correct in return, is deployed in the CM system, so an alarm shows up. So the trainee can actually see the interaction with the CM system. You see here that those rules, those CM rules in our case, are created with JSON, which looks not too nice, I think. The structure of this rule is that the top of it is the header of the rule, and then there are several rule blocks. Like you can combine several rules. Here you see only one. And of course, it's filled all with brackets and quotation marks. Now we use Google Walkway to facilitate this rule provision. Here it is a lot clearer how the rule is structured. Like you have the green header here, and underneath it, you can combine several rule blocks. Also, like on the left-hand side, you see one of our trainees making a mistake. He's like typing in the correct string, giving the rule the correct name, block call manipulation, but the rule is still not correct because he or she forgot the page mark. Here on the right, in Walkway, you don't have that problem. Finally, we conducted a user study with 30 participants as a randomized controlled trial, 15 of them using the traditional approach, creating rules with JSON, and the other 15 creating rules with Google Walkway. To do so, we defined 3 different types of pieces. The first one was regarding the learning outcomes. Do trainees learn more when they use a VTL instead of actual textual programming? The second one is concerning the learning process itself. So do they learn better? Do they find training more engaging and less stressful when they visually program instead of normal textually? And finally, regarding efficiency, do they learn faster when they use it? Does it take less time when they create rules in Walkway instead of JSON? And how we conducted this survey is now presented by my colleague Monty. Thanks.
To assess these 3 hypotheses, we chose a 4-step approach, beginning with a pre-assessment. The pre-assessment basically checks the pre-knowledge of the trainees. Then we conducted the cyber range itself. And after the cyber range, the trainee has to fill a post-assessment to test the knowledge after the exercise and to compare it with the pre-test. And finally, we gave a feedback survey to the trainee to check their engagement overall. The pre-test and post-test assessment was aiming at the training outcomes, so how much the trainees learn, and was looking like that. It was a multiple choice test where the trainees had to decide which answer is correct. And so we can check how many answers they had right in the pre-test and how many answers they had right in the post-test. To test hypothesis 2, that the cyber range exercise is engaging, and we used the TLX, the NASA TLX, the task load index, which was developed by NASA and basically was developed to test if a task is physical or mental demanding. And we adapted it to our approach to just check if it's mental demanding, but because our tasks are not physical. And so this part of the test is irrelevant for us. And as you can see, we tested this one after each task the trainee has to fulfill. And after that, he has to answer 4 questions, which was aiming at the mental demand of the trainee. In the feedback survey, we tested the overall engagement of the trainee and his motivation. with the ARCS model. The ARCS model basically stands for attraction, relevance, confidence, and satisfaction, and has those 4 dimensions after the experiment. To test hypothesis 3, that the cyber range exercise with the help of Google Blockly is more efficient, we measured the time the trainees took to do the cyber range and compare it to the JSON approach. Now I will go through the results and through each hypothesis and show you if we can accept or reject these hypotheses with the data we collected. Here you can see the results of the learning outcome. So on your 2 blocks, the Blockly experiment and the JSON group, and we basically conducted a t-test to compare the mean knowledge increase in the Blockly approach and in the JSON approach. On the left side, we have the knowledge categories. Each question which we asked to the trainees was assigned to a category, and in the last line, you can see the overall knowledge increase. And the interesting part here is the mean increase in knowledge. And as you can see, there is not quite that big difference between both groups. So the overall increase was 21% in the Blockly approach and 24% in the JSON approach. So there was a quite significant knowledge increase, but it's comparable in both groups. So we decided to reject hypothesis 1. To test if the trainees found the Blockly approach more engaging and more interesting, we assessed it with the TLX on the left-hand side and on the right-hand side with the ARCS model. On the left-hand side, it tests the mental demand. So low values are good because they're showing low mental demand during the tasks. And as you can see, in most tasks, the Google Blockly approach showed a lower mental demand, especially in task 1 and task 5, which was the introductory task and the most complex task. The Google Blockly approach performed quite well in considering mental demand. And considering the ARCS model, you can see that especially in the ARCS model measures the learning experience, and their high values are good because they indicate a positive learning experience. And as you can see in especially the attention category, the Google Blockly approach has much higher attention to the trainees. And that's why we accepted hypothesis 2. To test if the training is more efficient with the Google Blockly approach, we measured the time the trainees took to fulfill the tasks. And as you can see in both categories, in the Google Blockly approach and in the JSON approach, the mean duration the trainees took in the cyber range was around about 52 minutes, which is quite similar. So there is no real difference between both. However, we saw that there is a high number of outliers within our data. For example, one of the trainees told us that during the training, the doorbell was ringing, and he had to go through the door, and the postman was there, and he had to collect his delivery. So he had to pause the cyber range, which was a big outlier, and some also had technical issues. So this data is not really accessible. So we decided that hypothesis 3 is not accessible. To conclude, VPLs are a promising addition to cyber range training, and should be further investigated in the future. We showed that using VPLs is more engaging and less mentally demanding for the trainees, while receiving equally good learning results. And as a future work, we have to validate the statistical significance and investigate the potential of VPLs to different target groups. Because our target group are students who had a programming background, and in our opinion, the results should be more significant for maybe a target group that has no programming background and is just new to security and want to create CM rules, for example, but don't have a programming background. So thank you for your attention.